Hello all, in this video we will see the linear speed up theorem. See, the relevance of linear speed up theorem is that it says that speed of a Turing machine can be improved by condensing the characters into some k tuples. I'll show how exactly does it work. Before that, let me give you the statement. So linear speed up theorem states that if some Turing machine is performing some computation in t of n time, there is another Turing machine. If this is non-deterministic, the other one will also be non-deterministic, which can perform the same task in c into, where c is a constant which is greater than 0. So c into t of n plus n plus 2 time. That is, there exists another Turing machine which can perform. It is a multi-tape Turing machine with some t tapes. This also will be a multi-tape Turing machine with almost k number of t number of tapes. Yeah. So see, if a Turing machine is performing, a t-tape Turing machine is performing some job in t of n time, there exists another t-tape Turing machine which can perform the same work in c into t of n plus n plus 2 time, the maximum. So, where c is a constant which is greater than 0, so c is a multiplicative factor. That is, we can always speed up the work of a Turing machine. That exactly is linear speed up theorem. This is done by condensing the simples of a Turing machine. I'll show you how does it work. For example, if you have a Turing machine, for the sake of convenience, I am taking a single tape of a Turing machine. Yeah, it can be multi-tape Turing machine definitely. So I am considering only a single tape of a Turing machine. Okay. So if it is like this, A B A B like this, what I can do is I can condense the simples into a more condensed tuple format. For example, if I am condensing it into 3 tuples, I can write ABA as a single character, then BAA as the next single character. Now AB is the other character, like this. So if sigma is the alphabet here the alphabet should be increased, isn't it? Because now ABA is a single, ABA behaves like a single character. BAA behaves like a single character. AB behaves like a single character, because we have condensed these characters into single characters. So here we are taking the factor as 3, because 3 characters have 3 characters or 3 symbols have been condensed to a single symbol here. So the factor is 3 here. Now the alphabet should be improved so that along with the usual alphabet sigma, it contain all the strings of all the combination of symbols of size 3 or k in general. See, sigma raised to k is any any combination of 3 symbols from k symbols from the alphabet. If sigma is 3, ABB, anything can be written. Only the thing was the character length will be 3. The character symbol length is, string length is k here. So this will be the new alphabet. Okay. Now we will analyze the complexity of this approach. See, we are this first Turing machine has some n characters. We have to copy all these n characters. Then only we can paste them in the new. This is the new Turing machine M, and this is the new one that we are constructing, which is named M dash. Now all the n cells of data should be copied from M, isn't it? So the complexity has an n part, because we have to copy all these n cells from this tape. Now we have to copy them into n by k cells here, isn't it? For example, we have 1, 2, 3, 4, 5, 6, 7, 8 characters here. So we need 3 cells here, isn't it? For example, if 9 characters were here, 9 symbols were here, we need 9 by 3, that is 3 cells here, isn't it? So we need to copy the n simples into n by k cells in the second tape, isn't it? Now we have to bring the tape heads of both m and m dash back to the leftmost position, isn't it? For further processing. So this is the complexity that we will take. Now if we are analyzing it a little bit deeper to simulate m on m dash, what we do is, see, for a character, for example, if you are considering this b, okay, if you are considering this b, to get the characters, to get the nearby characters, it has to get the, the characters before, to the left of b is a, on to the right of b is a, and like this, isn't it? So to get the characters to the left of it and to the right of it, it may move to the left to get the left character, it may move to the right cell to left cell to get this character, it may move to the right cell to get the next character. For example, if you are considering this a, the next character is this a and it is lying on the right cell, isn't it? So you may move, sorry, to get this character to the left character, it has to move to left. Now to come back to this position, it has to move to right. Now to get this character, to get the characters here, it has to move again to right. Now to come back to the original position, it has to move to left, isn't it? So these four movements will be required to simulate m on m dash. That is, it has to move to left, move right so that it will come back to the normal position, move to right so that it can get the right character, now move left so that it can come back to the original position. So four such movements will be required, and again to make some changes that is required made by m. So m will be making one change at a time, isn't it? It will be overwriting some characters, replacing it with some other character, or do some kind of processing, isn't it? For that kind of processing, m dash may take at least one or two, maximum two steps, a right move or a left move, isn't it? So or both of them. So maximum two moves will be required for m dash to change, to make the changes in its state which are made by m. So a total of 6 moves will be required by m dash. Okay, so we can say that 6 into this complexity t of n, which is the complexity of the state. T of n is the complexity, 6 into t of n divided by k is the time it takes. That is, if k is higher, that is, if we have taken k as 3 here, if k is higher, you know that if you are condensing more simples into a single simple, the machine can work much faster, isn't it? So 6 t of n by k is the amount of time it takes for all these movements and all. So if k is higher, definitely you will require only a smaller amount of time. See, this is equivalent to using longer instructions in computers. Instead of many small instructions, if you are using a very long instruction, you can speed up the work a little bit, isn't it? So it's the same philosophy here. So now we have a constant c that I have talked to you about, isn't it? That is, we can create a Turing machine that works in c into t of n plus n plus 2 time, isn't it? So if we are substituting c as k as 6 by c, you can get this 6 cancelled and you will get eventually c into t of n plus n plus 2. Yeah, it is n by k, but at most n time. That is the maximum it can take, isn't it? N plus 2 time. So this work can be sped up. So that is the linear speed up theorem. You can speed up the work of a Turing machine by condensing the simples into characters by a multiplicative factor c, which is greater than 0. Okay, so that is it. That is linear speed up theorem. Hope you understood. Thank you.